Okay, so we understood in basic terms what is pressure. And just to clarify, when we talk about pressure as force divided by area, or talk it as force per unit area, it is generally the force which is acting perpendicular to the surface. Acting perpendicular, okay, not in any other direction to the surface. Okay, now that means in in the previous case when we were talking about pressure, we were giving the direction of force exactly perpendicular to the plane of the paper. If you see, this is 90 degrees, right? Similarly here also. So pressure is nothing but force acting perpendicular to the surface per unit area of the surface. Got it? Unit of pressure is because force per unit area, so force unit is Newton, area unit is meter square, right? So Newton per meter square. Other units are Pascal, so Newton per meter square or Pascal. Okay, and there are other units also of pressure like atmosphere. So other units of pressure are atmosphere, short for ATM. Then we have Torricelli. We have pressure expressed as centimeters or millimeters of mercury column. So we will understand all these whenever we come across these. But for now, we can understand that the SI unit of pressure is Newton per meter square or Pascal. And Pascal is written in the short form as PA. Okay, so these are the basic concepts. Let's move on further. Now, we will talk about the pressure in liquids. So here it's mentioned, if you read this part of the text, it's mentioned that solids develop something called shearing stress. Okay, so for now you understand this in a very simple way. If suppose there is a block of wood or a solid block resting on the table, and if suppose this bottom edge is fixed, or you stick it to the table so that this doesn't move, what is shearing force is force which acts parallel to the surface of this solid. Okay, surface of solid. What does this cause? This tends to shift the orientation of the solid. Now because the bottom portion is fixed, it tends to push the top edge, and if it's a block of wood it will not move like that, but if it's a block of sponge you can imagine, so it will move. Okay, with relative to this downward fixed position. So this is force which is called shearing force, and shearing stress is a related concept, force per unit area. Okay, for liquids this concept is not applicable because in liquids there is nothing like a shearing stress. If you apply a force parallel, the the liquid will not have anything like a stress sort of thing. Okay, the liquid will flow. Okay, so there is no concept of shearing stress in liquids. For now you understand this. When you go through the properties of solids chapter, you will understand this shearing stress in much more detail. Okay, so what is mentioned there is about this shearing stress concept. Liquids don't have this force and or stress. And suppose when an object, let us take a container, and let us say it is filled with a liquid such as water. Now if I submerge an object like a box or a stone inside this liquid, let us say I draw a stone here. So this is a stone. Now what happens is, now force, there is a contact. You can understand in molecular language, the molecules of the liquid are in contact with the solid right here. Okay, this is the solid surface, so everywhere it is surrounded by the liquid, so liquid is in contact with the solid and solid molecules are in contact with the liquid, so they are interacting on a macroscopic scale, that is a bigger scale, we can understand that obviously this liquid will be exerting a force on this solid. And how is this force getting acted? It's acted perpendicular to the point of contact. Let us, for simplicity, not take a round object. Let us take a square type or a rectangle type object to understand better. Now, on the top edge of this rectangle, rectangular block, the forces are acting like this, and the sideways it is like this. Okay, right? So that's what is mentioned here. When any object is submerged in liquid, the force exerted by the liquid will act normal, that means perpendicular to the surface of the object. This is the surface, top surface, so it will act perpendicular. This is the surface acting perpendicular. This is the surface acting perpendicular. Of course, the bottom, we are understanding that the object is, very heavy. It has sunk to the bottom, so there is no force due to the liquid at this edge, at this surface, right? So normal at all the walls. Then that's what is shown in the figure at all the points, on of the surfaces. And this pressure, when we talk about hydrostatic pressure, this pressure we talk about as again the same thing. Capital P as a symbol of pressure. So thrust is nothing but a force, perpendicular force, thrust upon area. Same formula which we learned earlier in general. Okay. And this pressure exerted by the fluid, because the fluid is at rest, water in this case is not moving, it's at rest in the beaker or tumbler. So this pressure exerted by the liquid on the object is called hydrostatic pressure. Okay, this is nothing but hydrostatic pressure. Okay, very simple to understand. And as we understood just a short while ago in the previous video also, the unit of pressure, SI unit of pressure is Newton per meter square, or you can write it as Newton, and when the meter square will be written on the numerator side, m raised to minus 2. Okay, or it is also known as Pascal, short form P capital A small. Okay, all good till here? So now let's understand how the hydrostatic pressure at any point in a liquid, okay, at any point inside liquid, okay, how the formula for this hydrostatic pressure can be easily obtained. Okay, so this is not to be memorized, it is just for your understanding purpose. So let us take a vessel, and that vessel is filled with a liquid. Let us say it is water. Okay, now we are imagining that there is a solid object which is submerged inside it. On the left side, you are seeing a cylinder. We can imagine a cylinder or any other three-dimensional object also. Let us say we imagine a cuboid. I think you know a cuboid. It is cuboid having the upper surface and the lower surface, which is a square. So let us just draw this. And let us say this cuboid's length is L, and this B and H are same. So we will just mention it as A side of the square. Okay, right? And it is submerged at a depth. Okay, not entirely at the bottom, but at the depth. So now, what are the forces? We saw that liquid exerts forces normal to the surface. On the top side, there is a force which is trying to push the object down. Similarly, at the bottom, there is another force which is trying to push the object up. Okay, right? What else is there? We also have weight of the object which is trying to push it down. So there are two forces acting at the top surface of the object which is submerged in the liquid. There is one force acting at the bottom which is trying to push the object up. Okay, these two forces are due to the liquid, so we will call them as, this force is normal force And because we have denoted pressure is equal to force per area, we can say force is equal to pressure into area. So this into symbol need not be written. We can simply say it is pressure into area. So that understanding tells us that this particular force exerted by the liquid molecules on or liquid on the top surface, we can say, let us say it is P1 is the pressure at this point at any point on the top surface, and A is the area. We can say area 1, but here if we see it's a uniform three-dimensional object, so the top surface and bottom surface are same. So let us say their area is, say, this is called cross-sectional area. So I will define it. A is cross-sectional area. Cross-sectional area of the solid. Imaginary solid. Okay. Okay. Let us imagine a solid like this. Now, what is cross-sectional area? Any three-dimensional object. This is the cross-section at the top. Similarly, there will be a cross-section at the bottom. Okay. This is not the total surface area. This is not the sidewise surface area. Cross-section. This top and this bottom. So anyone. So cross-sectional area is A. Okay. So P1 into A, pressure at the top point, into A is the force exerted at the top due to the liquid. Similarly, P2 into A is the force exerted at the bottom, the liquid. Where P1 and P2, P1 is pressure at the top surface of the block, solid block, and P2 is same pressure at the bottom surface of the block. Okay. Now, what is the net force? Because let us say the liquid is stationary and the block is just submerged in the liquid. Let's assume that. Okay, it's not moving, it's not even going down, neither sinking nor going up. So when an object is at rest, we know that Newton's first law says the forces acting on it will be in equilibrium. So that tells us that on one side, okay, this particular force which we said is the weight of the object, we will define that also. This is weight of the object, which we'll for now call as W. So I will say W is weight of the object. And we know weight is a force, right? We have studied that in the chapter on laws of motion as well as on gravitation, right? For those of you who don't know, we can understand weight as is force. So force is nothing but mass into acceleration. In this case, acceleration is the acceleration due to gravity g. So weight is nothing but mg. So now we will write the equation comprising the balance or equilibrium of forces. So we have P1A plus the W, which is acting at the top, both are acting at the top and trying to push the block down. They are equally balanced by P2A at the bottom. Correct? Otherwise, the object would have moved downward. So it is not moving downward or upward. So we are having this equilibrium. Now we will develop the equation further. We will say P1A plus what is weight of the object, mass of the object into acceleration due to gravity is equal to P2A. We will bring the pressure and area products on the same side, and we can say P1A. Okay, I will bring P1A to the right side. It will be easier. There will be no negative symbol. So I can write mg is equal to P2A as it is, and when P1A goes on the right side, it will become minus P1A. Okay, now we have A common in the two terms, so we will take it as common, and the uncommon terms we will write it within the brackets. P1, P2 minus P1 into A is equal to mg. Okay, right? Now, what is mass? M is nothing but mass of the object. That is the block, imaginary block we have understood. What is mass? We know that mass by volume is nothing but a physical quantity which is called density of the object. So mass can be understood as volume into density. Okay. Now what is volume? Further we can break it down. If I take about this object, we know it's a cuboid in our example. In that figure it is a cylinder, whatever it is. It is L into B into H for a cuboid. In this case, this B and H are same, so it is nothing but L into A square, or we can simply say cross-sectional area multiplied by this length. That is the volume. So L multiplied by cross-sectional area we have defined as A. So L multiplied by A is the volume, and density we refer to as symbol rho. Okay, density kg per meter cube is the unit. So density we use the Greek symbol rho for this density. Okay, now mass is equal to this. We will substitute the value of mass which we have written here in this equation. So this equation becomes, instead of m we will write L into A into rho, and then there is G here. This product is equal to, on the right side, P2 minus P1 into A. Now area terms are there on the left and right side, they will cancel out. So what remains is, I will rearrange the equation. It will be P2 minus P1 is equal to L rho G. Now what is L in this case? Generally we can say, because we are talking of this object is imaginary, in case of a liquid, let us draw this liquid here. This in the previous page we drew this picture. This imaginary block is inside the liquid. So we can replace this L, which is nothing but depth or height, H. So in that case, this will become, instead of L, H rho G, and here also we can write, instead of L, this can be written as H. So now if you see this equation, P2 minus P1 is equal to H rho G. Okay, so P2 minus P1 is difference in pressure. This is the pressure P2, this is the pressure P1. So difference in pressure uh, at a depth H. If I remove the object, this is an imaginary object. So the pressure at this depth minus the pressure at this depth. That's what we are calculating. So I will again draw this figure for clarity without the object. Let us say we are talking about the top surface of the imaginary object to be here somewhere. So let us say the pressure exerted at this point, and this point is having a certain depth. Okay, this is P1, and at the other point there is a pressure here. So this is at another depth. Okay, let us say this depth is H1, this depth is H2. The difference between these 2 points is our height H. If you see, this is H1 below the surface, this is H2 below the surface, and H2 minus H1. H2 minus H1 is this length, which is H. So we can say, for clarity, H2 minus H1 is H, and that is this H here. So difference of pressure at the bottom point and at the top point, which are separated by a height H, is equal to H rho G. Now extending this further, I will just erase this, and for clarity I will write draw a new figure here, a simple modification of the below figure. Okay, or I'll move this my image to the side so that it doesn't interfere with the drawing. So here I will draw a modification. Now let us say this object or imaginary object is not entirely submerged, but its top surface is either on the liquid surface, or in other case this top surface of the object is above the liquid surface. So now when it is in contact with the air, whether it is above the liquid surface or whether it is exactly at the liquid surface, the pressure or force acting downwards at point P1 is no longer due to the liquid, it is with the other medium in contact. In this case, it is due to the air. So it is pressure of air, or we call it as atmosphere. So we will say pressure of atmosphere. And this is pressure at H2, P2, or we can replace that by P. So now we have P instead of P2 minus P1 is replaced by P atmosphere equal to H rho G. Okay. And if you write this in terms of only P on the left side, so P atmosphere plus H rho G, height or depth below the surface, rho density of the liquid, and G. Okay, this rho was we will understand that later in buoyancy principle, but this rho is nothing but the density. This was an imaginary object, so we can now say H rho G is rho is the density of the liquid you are talking about. H is the depth below the surface. So we assume that this is the surface, so depth below the surface is H. Okay, density of the liquid, right? And G is the acceleration due to gravity. We assumed rho as density of the solid when we were understanding the imaginary block. It is the same in this case as the density of the liquid. We will understand that better when we follow the buoyancy principle, because when any object is submerged in a liquid, when any object is submerged in a liquid, okay, we will understand that the buoyant force exerted on the object by the liquid is equal to weight of the liquid displaced by the object, and that weight of the liquid displaced by the object will have formula mass of the liquid displaced multiplied by acceleration due to gravity, and therefore mass of the liquid is nothing but volume of the liquid displaced multiplied by density of the liquid, and that's how this rho is density of the liquid. We will understand that in detail, don't worry. For now you understand pressure at any depth h, at this depth h, from the surface is nothing but pressure atmosphere plus h rho g, because that is the derivation. Okay, got it? Okay, now that's what is mentioned here. If you see the derivation in the book, it's just developed on similar lines. Okay, now pressure atmosphere is generally taken as in atmospheric units it is called 1 atmosphere. Okay, in that case pressure at a depth is directly equal to rho gh. Otherwise, if suppose we are talking of difference in pressures in the case of submerged object, then the difference in pressure is equal to rho gh. Okay, so this is about the hydrostatic pressure at a depth in a given liquid. Now what is so unique about this is, as you can see in the left hand side different figures, I just move my image here. So now pressure does not depend on the shape of the vessel. It's very interesting phenomenon, right? So pressure is only depending on the depth. So if you see all these figures, okay, let's say the first figure is in the form of a cylinder, okay, the second figure is in the form of an inclined vessel, and the third is some other vessel where the neck is narrowed down at the top, and some other vessel which is in the form of a curve at the middle. So in all these cases we are only concerned with this depth. So if you see sorry, if I see, this is the same, assuming same for different vessels. So if I calculate, if I want to know the pressure at a depth here, maybe that is this point, same horizontal level, this point inside this, maybe the same horizontal, this point inside this, and same. So all we are interested in all these cases is what is the depth or height h from the surface, irrespective of the shape of the vessel. This is the same height because they are at the same horizontal level. So pressure at any point inside a liquid at the same horizontal level is same. It doesn't depend on the shape of the vessel, and that is a very good property, right? and it is useful for certain applications related to it. You will come across those in a short while. For now, you understand that pressure at a depth is nothing but, that is why the formula contains pressure at a depth H is equal to atmospheric pressure plus rho density of the liquid, g small g acceleration due to gravity, height, depth. It's not dependent on any area which is cross sectional or whatever. Okay, now we will see a numerical on the concept. Just refer to the bottom of the page, example 9.1. I have just deliberately hidden the solution. We will first work out this question and then see what is the solution provided. Okay, what does the question state? A cemented wall of thickness 1 meter, okay, can withstand a side pressure of 10 raised to 5 Newton per meter square. What should be the thickness of the side wall at the bottom of a water dam of depth 100 meters? Okay, take density of water as equal to 10 raised to 3 kg per meter cube and small g as 9.8 meters per second square. Now, here we need to know what is the information which is relevant to solve this question and what is just extra information. For example, the statement saying that cemented wall of thickness 1 meter can withstand a side pressure of 10 raised to 5 Newton per meter square is not exactly relevant to solving this question. Why? Because as soon as they say what should be the thickness of the side wall at the bottom of water dam. So at the bottom of water dam, and then they are giving us the depth of 100 meters. So we are focusing on depth h, which is given as, so I'll write it like this, given, okay. So what is given here? We have what should be the thickness of the sidewall. Let's first ignore that. Uh, Bottom of a water dam of depth. So depth is first our area of interest. So depth h is equal to 100 meters. Okay. Then density of water. Density of water is nothing but rho, which is given as 10 raised to 3, that is 1000 kg per meter cube. 1000 and 10 raised to 3 are same, okay, after 1 3 zeros. And what is our acceleration due to gravity? This is small g, okay. Its value is, we should generally know it, but it's generally given in the question also, especially for NIS level exams. So 9.8 meter per second square. Okay. Now let's calculate the pressure at the bottom. Okay, which is nothing but formula is H rho g or rho h g, however you want to write. H rho g. So H is nothing but 100 meters multiplied by rho is 1000 kg per meter cube multiplied by g is 9.8 meter per second square. Units are also very important to be mentioned, okay, along with the numerical values. Now 100 into 1000 is nothing but 1 lakh or 100,000. So if you want to write in scientific terms, this will be 10. So 100 will be 10 raised to 2 and 1000 can be written as 10 raised to 3. And we know that when the base is same and the numbers are multiplied, so the exponent gets added up. So 10 raised to 2 into 10 raised to 3 will give us 10 raised to 5. So let me write it here, 10 raised to 5, and I will remove this for avoiding confusion. So 10 raised to 5, these units I will write at the end into 9.8. So I will again write it as 9.8, which is this figure, multiplied by 10 raised to 5. The units are kg, meter into meter is meter square, per meter cube, and per second square. Now this unit will translate into Newton per meter square. We will see how it is at the bottom before we proceed further. Okay. So if I write kg out of this meter square, I will write meter on the top, and the second square I will take to the top, so kg meter per second square. This is the unit of force, we know that, right? So if I do this, what is remaining is there is 1 m remaining on the numerator side. I will write it with a different font color. So 1 m is remaining after you take 1 m, and then in the denominator you have meter cube remaining. Okay, now meter upon meter cube, you can see that it will be meter square. So now if you write this unit, then it will be kg meter per second square divided by meter square, which is nothing but unit of pressure, force per area. Okay, so this and this are same units. Got it? So let me just move my picture here for giving space for writing. Now we will again go with our original calculation. So what is the answer here is the pressure at the bottom of the dam is equal to 9.8 into 10 raised to 5. Can I say it is Newton per meter square now? Correct. Now let us read the question again. Cemented wall of thickness 1 meter can withstand a side pressure of 10 raised to 5 Newton per meter square. Now it is relevant, this portion. Why? Because we are asked to find the thickness of the side wall at the bottom of a water dam that is having this much pressure, which we just now calculated. So that wall has to sustain that pressure. So it's a question of ratio, proportion, or unitary method. So what's it mentioned is there is a pressure of 10 raised to 5 Newton per meter square. For withstanding that pressure, the thickness of the wall needs to be, is the mentioned the question is 1 meter thickness. A cemented wall of thickness 1 meter can withstand, right? So this is 1 meter. So I will use the symbol of ratio here, and then proportional. So 10 raised to 5 Newton per meter square is to 1 meter. So as the pressure we calculated is 9.8 into 10 raised to 5. It is 9.8 times 10 raised to 5. So 9.8 into 10 raised to 5 is to how many meter thickness? X meter. It's a very simple proportion, ratio proportion calculation. But for those of you who don't understand the ratio proportion or who have forgotten that, let me just illustrate it on the sideline. This is written as A is to B, so as C is to D. In fraction terms, we can write it as A is to B is nothing but A by B, and this so as we can write it as equal to C by D. So now I think you understand this language. A by B is equal to C by D if I write. So I can cross multiply. So A into D. If D is in the denominator on the right side, when you take it on the left side, it will become part of the numerator. So A into D. Similar is the case with B. If B is taken on the right side, it is in the denominator on the left side, it will become part of the numerator on the right side. So AD equal to BC. So whenever I write this proportion, I can directly write A into D equal to B into C. Or rather, we can understand it in this way. The middle terms get multiplied, and that multiplication product is equal to the product of multiplying the extreme terms. Now, coming back to the question, so middle terms are these two, and extreme terms are these two. So we can say 10 raised to 5. I will not write the unit here initially. So into x Newton per meter square into meter is equal to 1 into 9.8 into 10 raised to 5. Again, this is also Newton per meter square. I forgot to mention here. So Newton per meter square into this meter will come here. So basically the units will get cancelled out. Okay, right? Now instead of x meter, I will just write x because I don't know. So that finally when we calculate, we should have x. So here I will not write, one second, this and this. So I will write Newton per meter square, and x we will keep it as it is. We will get the unit. Okay. So here Newton per meter square will get cancelled with Newton per meter square. There will be a meter term on the right side open. So I will just rewrite it so that you can have a better understanding. 10 raised to 5 into x equal to 1 into 9.8 into 10 raised to 5 is nothing but 9.8 into 10 raised to 5, and this m, small m, is there here, so meter. Now if x I want to find out, basically it is 9.8 into 10 raised to 5 divided by 10 raised to 5 and meter. This gets cancelled out, so 9.8 meter. We can directly address that, because if the pressure to be withstanding is 10 raised to 5 Newton per meter square, for which the wall thickness is 1 meter, pressure is 9.8 times of that, so obviously wall thickness should be 9.8 times of 1 meter, which is 9.8 meters. Very simple calculation. But just for you to be able to understand how the calculation can be done or needs to be done if there are different values, I have processed the question solving in this way. So x is nothing but 9.8 meters. So this is the thickness of the wall at the bottom of the dam, which is required to sustain the water pressure. Let's now check the solution mentioned in the book and see if it tallies. So here it's mentioned pressure on the side wall of the dam at its bottom is H into D into G, or rho into G. D is density here. So 100 into 10 raised to 3 into 10, 9.8. So 9.8 into 10 raised to 5 Newton per meter square, which is what we got here, pressure at bottom. Using unitary method or ratio proportion method, we can calculate the thickness of the wall. So for withstanding 9.8 into 10 raised to 5 Newton per meter square, thickness of the wall required is 9.8 meters. So I think we got the correct answer. Okay, so we have solved a numerical related to hydrostatic pressure. In the next video, we will understand about atmospheric pressure and then the further concepts in this chapter.